Okay, so Leon Chua is I think he's Filipino, Chinese, and American. So he studied here in the Philippines in, I think, 1960s. So he graduated electrical engineering at Mapua University. Chua circuit is very ubiquitous in studying chaotic systems. It's like that pendulum system. It has 3 fixed points, but all of those 3 are unstable. So my goal was to stabilize the system in one of those 3 points.
Okay.
And then the third one is the origin, or such that the 3 states of the system are 0. That one is the most challenging to stabilize. It is very complicated, for example. But I was able to stabilize the system the best using the sparse identification model. Sparse identification uses machine learning to generate the mathematical model directly from measurement data. Fractional calculus has already been around since the 1600s, and they are able to use it in a lot of industrial applications like the fractional PID, but until now they haven't yet defined it. So can we really say that we understand what a fractional derivative is? We're not able to define it.
Hey, I'm Al, and this is the Paglalayag podcast. I'm using this podcast to showcase what's going on around me in the hardware and cleantech sectors dito sa Philippines. With guests from across the startup, research, investment, and enabler ecosystems, Paglalayag focuses on the stories and inspirations that motivate us to start up in hardware and press on down this arduous path of steering our economy away from the looming climate catastrophe that makes itself increasingly felt in our lives each passing year. I hope you'll find this cast of characters as impressive and inspiring as I do. Also, if you've been listening to these podcasts and want to let me know what you think, there's a survey form available at paglalayag.net-podcast. You can also reach out by email at al@paglalayag.net. I'd love to hear from you. Sige, tuloy-tuloy lang. Let's jump in.
All right. So welcome everybody to Paglalayag. I'm Al. And this is going to be a chaotic episode with Mark Justine Domingo, who's just completed his master's on a topic called sparse identification for fractional order model predictive control. So this is using chaos theory for electronics, and we're going to get into it and get into all sorts of chaotic maths for this episode. So thanks for joining me, Mark.
Good morning. Hello, Alan.
Yeah, so thanks. Why don't you start out just by telling me a little bit about the project overall and what got you interested in the topic and high-level overview of what you did.
So my topic is the sparse identification for fractional order model predictive control. So it has 3 parts, so the sparse identification part, the fractional order, and the model predictive control part. So I got interested in that because fractional systems currently one of the research topics that few people are studying about that.
And fractional order is similar but not exactly the same as fractals. Most people, if part they would recognize the most is like fractals,
yes,
which can make these really amazing pictures. But it also has all sorts of applications in different fields of mathematics and physics and engineering.
Yes.
So
yes.
What we're talking about electronics here.
Yes. Specifically, fractional order model predictive control.
So yeah, and control systems, like, I mean, you could just think about like a toilet filling up with water, and then when it hits the level that it's supposed to, then the floating piece will close the valve.
Yes.
That's like maybe one of the most simple examples of a control system.
Yes.
But when you get into electronics, it gets much more complicated.
Yes, absolutely. Another example of a control system is when you are driving, and then, for example, you are trying to go straight, and then you are trying to control the steering wheel so that your vehicle will not drift to the right or to the left. That's another example of control system. So there are a lot of control systems around us, even in our bodies. How our body regulates the production of insulin, those kinds of things. But for electronics, we have control systems for controlling the voltages and currents in power systems. We have control systems for controlling the trajectory of spacecraft. There are
Definitely. So we've talked about the model predictive control is sort of it's you can think about it from with models in the same way that they talk about AI models, but not necessarily.
Yes, it's not necessarily AI. Although some researchers are now trying to see the connection between reinforcement learning and model predictive control. But the difference with model predictive control is that you are using a mathematical model of the plant you are controlling to control it. You are using mathematical model, unlike reinforcement learning, where you have to train the system. In model predictive control, you don't have to train anything. So
the father of reinforcement learning was Sutton, and he talked about in the precursors to neural networks dynamic programming. You might consider this more closely to dynamic programming.
Yes. So it is really related to dynamic programming by Bellman, by Richard Bellman.
Okay.
Because when you are trying to generate control signals using model predictive control, you are always optimizing something. So dynamic programming was made to optimize something. For example, if you have a cost function, but what I say by cost function is that, for example, you are trying to minimize the time that it takes for your system to reach a certain point. That's a cost function. Another one is, for example, you are trying to minimize the amount of fuel that you are expending to control your system. That's another cost function. So through dynamic programming, you can optimize that, and then that control signal will be used in model predictive control.
And this is where sparse identification is that optimization process.
Not really, because a key part in model predictive control is that you need a model. However, for some systems, we can get a mathematical model of that. For example, you will use physical laws like the Kirchhoff's laws, Newton's law of motion. So for some systems, we cannot do that because it is very complicated, for example. But using sparse identification is a machine learning algorithm. So it was developed by Stephen Broughton and his colleagues in 2015. So it uses machine learning to generate the mathematical model directly from measurement data. So from that measurement data, they are able to get mathematical models similar to the model you will get by modeling it theoretically. So that's the purpose of sparse identification.
Cool. And so this isn't 100% modeling. You did some modeling on the computer, but you also were working with a hardware circuit, and it was a chaotic hardware circuit.
Yes.
So why don't you tell us? We'll go a little bit into the background first, and why don't you tell us all who Leon Chua is?
Okay, so Leon Chua is I think he's Filipino, Chinese, and American. So he studied here in the Philippines in, I think, 1960s. So he graduated electrical engineering at Mapua University. And then for his, I think it's on the 1970s that he discovered theoretically the existence of the member store. So a member store is a device that relates the flux to the charge of the device. So after that, he was able to create in 1983 the Chua circuit. So the Chua circuit is the simplest electronic circuit that is able to generate chaotic dynamics. So that's why Chua circuit is very ubiquitous in studying chaotic systems because it is easy to make, and then you really only need a few parts for it to work. And then from that you can perform a lot of studies and experiments.
Yeah, so he was really operating like in the time that people were first starting to become aware of these nonlinear systems that they're chaotic in nature, like the Lorentz. He would be a contemporary of Lorentz when he was doing his studies about weather systems, and Mandelbrot when he was starting to describe fractals. Chua was very much applying these new techniques and new found equations in electronic circuits, and he developed this Chua circuit and also the Chua diode, which is kind of a key component of this chaotic system, by making the diode itself non-linear in both directions.
Yes. So the Chua diode is essentially a negative impedance device. So what I mean by negative impedance, that for example, you have a resistor. If it is not a negative impedance, it's just like a normal resistor. So when you put a positive voltage, then positive voltage across its terminals, then the current will go along that from the positive to the negative direction, right? But for negative impedance components, it will go the other way around. So it's called negative impedance. Like it has a negative resistance. So the Chua diode is a key component of the Chua oscillator because it allows for the generation of the oscillations, because it's essentially supplying the energy to the oscillations.
Yeah, so that's quite a interesting device. I mean, I've never heard of it in industrial circuits or anything like that. I'm not sure to what extent it gets used today. Have you heard about it getting used in practical applications?
In practical applications, I'm not really sure if there are any. It's not really a device. It's not really, for example, you have resistor, it's not, or a capacitor. You can build it using, for example, 2 op-amps. You can configure it in such a way that it will behave that way. That's why I think you haven't heard about it in industrial setting.
Right. Yeah. It's sort of a theoretical device. I mean, you think of diodes, and diodes just usually when people use diodes, they only want current to be able to flow in one direction. Whereas this has a very different behavior to it.
Yes.
So. Because these chaotic mathematics and stuff have really, like before these maths started to become known, everybody in physics and stuff would kind of believe that if you understood a system well enough, then you could understand it completely and you knew exactly what it was going to do.
Yes.
And then one of the things that really disrupted that was these new kinds of maths, and especially the what they call a sensitivity to initial conditions. So why don't you explain a little bit about how that works and how that applied in your project?
So sensitivity to the initial conditions is one of the hallmarks of chaotic systems. So what do you mean by that? For example, you have a system, then the initial conditions is, for example, 1, 1, 1, and then you watch it behave this way. For example, it will go in a parabolic path, something like that, and then you change the initial conditions by a little bit. For example, you turned it to 1.000001 and then 1 and 1 for the states. You will watch it behave a bit parabolic at the first, and then you will watch it immediately go spiral. In other words, it will behave very differently than the previous trajectory. So that's the sensitivity to the initial conditions.
Like similar to why like weather forecasts will only ever forecast maybe a week in advance, because you just don't have that level of prediction. Things change so much, what people like to call the butterfly effect.
Yes. So the butterfly effect, so they compared it to the, for example, there's a butterfly in Mexico, and then it just decided to randomly flap its wings for no reason. And then that small change will cause change in the initial conditions of your weather system. And that small change will cause a very large tornado to occur in the Pacific. So that's why they call it the butterfly effect.
Yeah, definitely. And so we're talking about electronics right now, which are smaller systems but still very complicated, and the different things in there can change very fast. And so in your case, you had this oscillator,
Yes.
which is it seemed like is oscillating like maybe 4 times a second, 4 hertz.
Not really. Yeah, because I designed it to be very slow so that I can apply control systems easily. I can use a controller easily. That's why I designed the dynamics to be slow.
Right.
Okay. So it's not really. It's called a chaotic system because the trajectories are different.
Well, you've got a diode, a Chua diode in there that is sometimes letting the current go in one way and sometimes letting it go in the other. So
Yes.
you've got these different parts of the circuit that are oscillating sometimes, and
Yes.
and the amount of oscillation that's happening in any given part of the circuit is fluctuating
Yes.
in a very unpredictable way.
Yes, it's the thing is that so it is very unpredictable because in the Chua circuit there are 3 energy storage elements. So there are 2 capacitors and then 1 inductor, and then the energy in the circuit is randomly getting stored in those 3. So it's getting stored in the electric field of the 2 capacitors and then the magnetic field of the inductor, and it's behaving really unpredictable. Although it can be modeled using a mathematical equation, you cannot really predict how the energy will be stored in those 3.
Right, and then to go even one step more complicated, you've introduced this fractal or
Yes.
fractional capacitor.
Yes.
Yeah.
So the fractional capacitor, I have a Chua circuit, right? So I changed one of the capacitors to a fractional capacitor. By fractional capacitor, what I mean is that it is governed by fractional calculus instead of integer order calculus. So what is integer order calculus? So in a normal capacitor, we usually model it as the current is proportional to the first derivative of the voltage, right? But in a fractional capacitor, it can be modeled as, for example, the current is proportional to the half derivative of the voltage instead of a whole derivative. So the difference with fractional capacitor with a normal capacitor is that its dynamics is dependent on the history of the capacitor. So for example, its charge yesterday is around 0.1 coulomb. Its dynamics now will be affected by that 0.1 coulomb charge. Unlike for normal capacitors, that it will only be dependent on its present state. So
it's got kind of a memory to it.
Yes. That's what separates fractional calculus from integer order calculus and fractional systems from integer order systems.
Yeah, so hopefully our listeners are getting a sense that this is quite a strange system. So if you're going to try to model it,
Yes.
there's a lot of different things you have to be taking into account, and this model is then, if the model is then going to predict what the system's going to do next,
Yes.
in order to try to influence what it will do next, because
Yes.
that's the control part, that's the act. Then that's a very tricky mathematical problem. So what they did in the past with non-fractional systems, I understand, is called Cindy, right?
Yes. So Cindy is a machine learning algorithm that lets you get the mathematical model directly from measurement data. So it essentially models the system as a set of first-order differential equations. So, by that framework, it is limited to first-order differential equations. The problem with fractional systems is that
They're not first order.
yes, they're not first order, so they can be 0.5, 0.98, something like that.
First order would be 1, second order would be 2. That's when you've got like
Yes.
a x squared, like a parabolic, or
Yes.
or along those lines. But then, yeah, when you're going fractional, then you've got some kind of number in between, which just makes for weird
It's really
computation.
weird. Because what makes it weirder is the fact that researchers cannot agree yet on how do you define a fractional derivative. Unlike for example, you have a first order derivative. What you mean by that is the rate of change of that quantity you are getting the derivative. But if you get the half derivative, you cannot say that it means that it is the rate of change. Okay, so that's really weird. So that if you will try to study that, you will see a lot of definitions for fractional derivative. There's the Riemann-Liouville derivative, the Caputo derivative, Grunwald-Letnikov, then there are a lot of other things.
Yeah, so this is still very much, people are trying to wrap their head around kind of a way of talking about this that is kind of consistent and captures the dynamics well of what these numbers mean.
Yes.
But you can still sort of produce hardware that does it.
Yes.
But even just to talk about what it's doing is still challenging.
Yes. And the funny thing is that physical systems really are fractional. So, for example, you have a capacitor, you just get a capacitor from the market. It's not really first order because all things are influenced by their past, I think.
Right.
But we are using the first order models because we have tools to solve them.
Right. Yeah, if it's a linear system, you can do that by hand.
Yes.
And as your systems get more complicated, you can handle that with computers or whatever. But
Yes.
if you can't even do if you can't even calculate it linearly on a basic component level, then it's very hard to scale those complexity.
Yes. I think some other things are really better solved using integer order than fractional because fractional calculus makes things really more complicated. And some other things, their fractionality is really very low. That's why using integer order calculus is easier and more practical.
Yeah, definitely. So then kind of the last piece of your thesis was to try to be able to stabilize the system.
Yes.
Like you've got this very dynamic, unpredictable, even more unpredictable because of the fractional capacitor.
Yes.
And you now making this model that's going to try to predict the thing well enough that it can stabilize it.
Yes.
And I think that appears to have been quite successful.
Yes.
With the approach that you took.
Yes.
And these are like adaptations of existing models. So why don't you tell us about that?
So what we did is that we extended this SIMD algorithm or this sparse identification of nonlinear dynamics. So we extended it by introducing fractional order. So for the original SIMD, it's modeled as a set of first order differential equations, right? So I thought, why can't we put fractional orders in the left hand side and then let's try to see if it will model the system better. So after using that, after several trials on different optimization algorithms involving the L1 node, I was able to get the fractional differential equations that actually model my fractional Chua oscillator. So I was able to get the mathematical model of the fractional Chua oscillator directly from measurement data. And then using that model, I put it in a predictive control algorithm. So using that measurement, I was able to generate control inputs by using a predictive control algorithm. So
But this is still all numerical, right?
Yes.
Even though you got the data from a hardware Chua oscillator, you have not tried to put a real actuator on and use that model to stabilize a physical circuit. Is that correct or no?
My Chua oscillator has a built-in actuator.
Okay.
So I controlled it in the actual hardware. So it's essentially a voltage controlled current source.
So you've got this system that will be very unpredictable, but based on the measurements that you're taking of the system, you're able to flip the control and move it into the state that you want it to be in.
Yes. So my goal was to stabilize, because a Chua system has 3 stable points. So what my goal was to stabilize the system in one of those 3 points.
Okay.
And then I tried to use the same predictive controller using models generated by nonlinear function optimization with genetic algorithm and with my theoretical model of the system. So I also modeled the system by hand through Kirchhoff's laws. And then I have 3 models. So I have the model using the sparse identification, using theoretical laws, and then using nonlinear function optimization with genetic algorithm. And then I used the 3 of them in predictive control. And then I was able to stabilize the system the best using the sparse identification model. So that's how it went.
Cool. So what do you think you would try to do if you were to keep going with this? What do you think you would try to do as a future step?
So my current plans is to try to use it in anomaly and fault detection. So for example, we have a industrial plant, and then we have a lot of sensors. So we are logging the sensor measurements. So how do we know if the system will have a fault? So there are already a lot of studies that are working on that, but they are only using integer order models. So the advantage of using fractional order models on that is that you will also incorporate the historical values of those sensors. So it's in a sense gonna be more accurate than the integer order.
Very nice. So in your kind of plant control systems and actuators, you would seek to try to do this model predictive control. Would it be something that's coming that's done on the device itself, or would it be because control is a moving target, right? You might need to turn the control amount up and down, and that would be coming from some kind of management situation, right? So how do you see that playing out? Like where is the model sitting? Is it on the device itself, or getting different instructions, or what do you see?
It's not really going to be in the device itself. So for example, you have a SCADA system, supervisory control data acquisition system for an industrial plant, and then you are logging the sensors in a computer. And then there are some errors or faults or anomalies that are not going to be detected immediately. But so this system will be put on that centralized supervisory system, and then you will somehow be able to predict when the error will occur based from the historical data of the sensors.
When you say error, you're saying error that might contribute to a fault situation in the future.
Yes. For example, you have several disturbances in the system that are unaccounted for, whose effects are not immediately seen, but will eventually affect the system in the future.
Right. Cool. I'd known that you were working on this stuff, but after reading it, I was actually quite pleasantly surprised. It's quite an interesting project, and it's good to see that it kind of worked out, like that you managed to actually make the stabilization. You described to me at one point like the pole balancing situation. Like if you've got a pole on a hinge, it could be stable if it's hanging down, or it could be stable if it's positioned perfectly upwards.
Yes.
But that's a very sensitive, stable position.
Yes.
The 3 points in the Chua oscillator that you're dealing with, how intrinsically stable are they compared to that kind of very simple example?
So the Chua oscillator is like the pendulum system. The difference is that it has 3 fixed points. We call it sometimes equilibrium points or fixed points. It has 3 fixed points, but all of those 3 are unstable. So if you put, if you are somehow able to induce your system such that the voltages and currents are in those 3 points, any small change or any perturbations in that will cause it to deviate far away and lose stability. So my controller was able to stabilize those points. So I was able to generate control input such that the state of the system are fixed on either of those 3.
Okay, so they're all. Would you say they're all equally challenging to stabilize, or there's one that's more challenging than the others?
Honestly, there are 3 fixed points, right? So one of them has a positive voltage for the capacitor, another one is the negative voltage for one of the capacitors, and then the third one is the origin, or such that the 3 states of the system are 0. That one is the most challenging to stabilize.
Okay. Just almost to get it to turn off.
Yes.
To get okay, interesting.
So the implication of that is that you don't really want chaotic dynamics in some of your system, right? Because you want your system to be predictable if you are designing something. So I was trying to stabilize that in that 0, point, so that there are no chaotic dynamics. So that was my challenge.
But of course, the world around us is very chaotic. So the ideal of not a chaotic situation is probably not a reasonable assumption in a lot of problems. I mean, if you're just talking about a simple circuit, sure, you can control that. But
yes.
But the much bigger world is going to be chaotic, regardless of what you want.
Yes, absolutely.
So I've got. So I always finish off the episodes of Paglalayag with a couple quotes. So I'm going to ask you to comment on a couple of these. So the first one is from James Gleick. James Gleick is the one who wrote the book on the history of chaos and the science and everything. So James Gleick, he said, you don't see something until you have the right metaphor to let you perceive it. And then the second one, being Carl Jung. Carl Jung said, in all chaos there is a cosmos, in all disorder a secret order. So what do you think about those 2 statements?
I think I heard that statement already by Carl Jung. So from that quote by James Gleick.
Yeah.
So it means that everything is just our perception. I think it's somehow related to our language. And is he a linguist?
He's a historian. He might be a bit of I think he's more of like a journalist historian. But this one came right out of the book about chaos. Like he would start each of his chapters with a little line.
I somehow agree with it, because unless we are able to describe something using terms that we understand, I think we don't really understand the thing.
Yeah, well, it's amazing. It's amazing to hear that that there's still many different definitions, and people have not yet. The specialists of the field have not yet come to agree on a definition for fractional order. Derivatives. Yeah, that I mean that this is what 60 years now since Chua started presenting these circuits and making these kinds of predictions of new devices.
And the funny thing is, fractional calculus has already been around since the 1600s, and they are able to use it in a lot of in industrial applications like the fractional PID. But until now, they haven't yet defined it. So can we really understand? Can we really say that we understand what the fractional derivative is? We're not able to define it.
Right. Yeah. PID being another class of kind of control systems that can be applied and are applied in a lot of different real world applications for sure.
Yes.
Cool. Well, I think that's it. And so this is the kind of stuff that's going on in the electronics research at BSU lately. I was quite surprised to see a project like this. Very, very nice one. So good, congratulations with what you've been able to do, and would be interested to see where you go from here.
So thank you very much. I apologize. I did not explain the things very well because I was struggling to explain it in colloquial terms.
Yeah, there's a lot going on with this stuff that it's not so easy to explain. But hopefully, as a listener, you can at least kind of appreciate why this stuff's so interesting. So yeah, all right. Well, tula lang. Thanks a lot, Mark, and we'll let you go from here. Cheers.
Thank you very much.